done. Good morning, everybody. Today, to talk about shape analysis and images, and we're getting closer to what we really want. So, let's see if I can get my mouse in the right spot. So now it works. So we wanted to quantify things, and for example, we want to know how big are the shape is, maybe also comparing different sizes, and and in the long run also comparing images of different types or different measurements and see what happens. And then with these statistics, the first step we need to do is to characterize our object. To do that, we need some that I'm going to talk about today. And we have our objects. We can, for example, measure volume. We can look at the center of gravity, its boundary, also anisotropy of the objects. So there is a lot of options you can look at here. And until now in the lectures, we have at the acquisition. Then we got a lot of data. In this example that's mentioned here, we have 56 gigabytes of data. We can't do anything, so we do some filtering. That still leaves us with 56 gigabytes of data. So we are now up at 112 gigabytes because we don't throw away the original data. And it's a lot of data to work with. Then we do the segmentation. The segmentation, we mostly split it down into very few classes. So every pixel maybe is a thing or is not a thing. So then we only need a single bit to describe this. And then we can reduce the to 1.275 gigabytes. And that's something you can start working with in any today. Some years ago, even 2 gigabyte was that you couldn't come past. But now most computers have 8 gigabytes and more, so that wouldn't be a big problem. But the 56 is still something you need to use with. Still, with segmentation, we are not quantifying anything yet. We just know that we have black and white pixels, but they don't. So now we want to look into what do we want to know. We want single numbers. We want, for example, volume fractions. How much is or is material we want. Could also be that we want to count objects between images even, or different experiments. Maybe we want to know the average cell stretch or volume, things like that. And in principle, what we're looking for are things like these. Find hidden objects is one thing. We want to know dimensions and the counting, also mixing ratios, sizes of things. How much is there of this kind? How much is that of other kind? And something that we will look in later lecture is also changes. So if you have a time series, you want to know if something is changing, if the size is changing, if the spatial distribution is changing, or things like that. Could also be that the color is changing. Color is actually something that I'm not touching very much in these lectures, but it's actually also a parameter that you can. The metrics we can look at are surface area. So we can look at shape tensor that describes how it's oriented and what the shape is. We can do some principal component analysis from that. Also looking at the anisotropy. Actually, I realized that these three should actually be shifted in because they all go under the label shape tensor. Then we can have some scale-free metrics describing these objects. So if you have a blob in a certain shape, important thing is that it has a specific shape. Then there are a couple of things that are more as a introducing step to doing other kind of analysis. So meshing and meshing is a way that you can describe a surface with the help of mostly triangles, and or you can also describe it the whole volume using tetrahedrons. And with that, you can then use the information to plug it into, for example, finite element analysis. Or you can also use it just for, oops, I'm lost somewhere. Hello. Ah, my mouse is on the wrong. You can also work with visualization, so talking about isosurfaces, it's also something that we could use these meshes. So, a lot of literature as usual, and in principle, look into the topics that you are interested in. These two are good starting points. The theory part here is good. The language choice is not mine, but anyway, it's a very popular analysis, statistical analysis. But honestly, I have never worked with R myself. So, but the theory of what you can measure is still valid and good to read about in that book. And then we have something about principal component analysis. That's a whole framework actually, so it's quite a lot. It's just a sub-chapter in that book. And yeah, then there is a lot of other things about shape tensors that you can also look into. As usual, this is a notebook, so we need some modules that we need to load. And in this case, most of it is known. The only thing is, for example, here we have from scikit-learn, we have principal component analysis. The neighborhood classifier we already know. And this is just for the graphics. Yeah, I think, there is one new too. Region props. That is also something that we will. And this was a bit low, but component labeling. Until now, we only had a black and white image or bi-level image. See that we have 3 objects. Computer doesn't know. So what we need to do is to do some kind of labeling, and that is an algorithm that goes over the image and puts a label, a number, on each item in the image. And that is what you see down here. Now instead of all bright, you have now 3 different colors and a background. What the code is doing is just create these blocks here, and it's nothing so exciting as such, but we're using this label function, which you can find in morphology. And just to test it, we have an image here. That's someone already did. We have some cars, and I think the original task for this image was to identify where the cars are. Now, for the segmentation, because that is cars or fraction of cars. So, for example, this one is hidden behind a traffic sign that you can see here. These are from Latin. That one, but everything is marked up as cars. So, for this exercise, we are interested that we have different pieces in the image. And when we work with this label function, and talk about, again, different neighborhoods, and that's actually why I brought up the manual. And you can see you have 1 connectivity or 2 connectivity. I usually refer to it as 4 connectivity. But principle, what the one connectivity here means is that it only looks along the principal directions. So you only have 4 neighbors around for doing this labeling. I don't know really when to use that one, but it's also an option. Some algorithms probably need it. But one are these two. And why we need this is that for doing the labeling, it's to, actually we can go on to the next. Yeah, it comes in a few slides when I explain why we need neighborhood. But anyway, if we call the labeling on these car images, you can see that we get different colors for the cars. And the interesting thing is over here, where you can see that the cars that are split up by obstacles, they actually turn into labels because they are disconnected. And that is that it identifies and puts labels on isolated objects. It has no intelligence objects together. And with area calculations, so in principle, what the area is for every pixel belonging to an object I, we just sum it up. And that can be done in different ways. One is through some Python coding, which I brought up here, where you have the labels and then you ask for the unique items. That's actually quite handy function in Python, in NumPy, that you give it a data set and then it returns a list of all unique values in that list. So if, for example, you have a large image and in our case we only have 10 items, it returns out a list of 10 numbers which correspond to these items. Then I loop over these labels and append them to an area vector, and now for the visualization I put them in a data frame and I show it. This transpose is just to flip around the table as this. And we can see that we have some counts for each object. Some are small, some are large. And this is one way of doing it. And sometimes this is a good way. Your labels have putting them in a nice sequence, then this approach could be good. If you know that you have labels in a sequence without any breaks in it, then you can use the histogram, because the histogram is actually how many you have of each object. In this case, you need to know how many labels you have in the data. And then you say that the histogram should have so many bins. And then it counts nicely. Or every label, it counts how many you have. So this is to calculate it. Then you don't have to do any multiple loops, because this one is less efficient because it has to go through the image as many times as you have labels. This one, the histogram, does only one single count, and that can give you a speed up. So, how do the component labeling algorithm work? In principle, what we do is we start with our black and white image. And this is what we have here. We have background pixels labeled 0, and we have foreground pixels labeled as 1s. Now we do some initialization that every pixel gets a number. And the number is just a sequence given by its position. So it's here you have x plus y, y times the width, and then you get the numbers as a long sequence. This can also be done in different ways. Here I show the loop version. You could also do it, and you create the x coordinates and one with y coordinates, and put them together. And that is probably the fastest solution, because as soon as you do loops in Python, you're lost, time-wise at least. Because loops, they cost. So if you can use the matrix operations in Python, do it. That is the first optimization advice when you work with this kind of languages. The algorithm itself, now we have initialized, we have all pixels, got an initial label, but that is not what we want. We had here now in this, each pixel, not each object, has its label. And now we want to bunch them together in groups that have the same label. What we do is we go through the image step by step and look for each point that is not background. We look in the neighborhood and we give the pixel we are looking at the minimum value except for 0, which is we give that value. So looking around, okay, here I found it. So going back here in this example, if you are here at 11 and look around, now we look at the 8 neighborhood, look around, we have 0, 0, 0, 12 is still greater than 11, so it's still an 11 going around, and then at the 1, it's less than 11, so what we will do is to give this pixel the value 1. And then we go through all the in this way, and finally we have our labels. And that need to be repeated a couple of times until you have stability. And the code for that looks quite long. We have essentially find which pixel we are working at and to look at the neighborhood around the pixel. And in principle, we go through here and looking at the pixel. Is it greater than 0? Then it's foreground, and then we go into this loop. And going much more into detail about this, but at least if you're interested how a symbol work, this is the way to go. There's some ideas about. Oh no, I just give you some references. Sorry. In this, you can see now, as I said, in the iteration. So the titles here are not updated apparently. So you can see after the first iteration, we have ones here because they are the minimum. And interesting. No, this is during iteration 3. Okay, that is it. And then you can see here the 49s, they get their labels, the 51s get the labels here, and the 9s get the labels here. Then you would go to the next label, and then you can see that the 1 is propagating down this diagonal. The 49 is propagating up this diagonal, the 9s are propagating up, and the 51s are propagating down. So during iterations can also be visualized with a little movie, where you can see how this so-called brush fire is expanding out in between the pixels. This was a quite simple example, but it shows at least how it works. And this one converges quite quick in this case. If you have large images with more objects, with more complicated objects, it can take right. And there are down the image and once back through the image, and then you have your label. This one is actually quite an old paper, so people were smart before they were. And another one, fire, is the one that is described here in this book. That's more or less doing finding an object, and then it does some region growing within that object until it's complete, and then it goes looking for the next object and region in that. Which is more efficient? I haven't actually timed it, so I can't tell, but I think both have their benefits. Now let's look at a bigger image. One of the cars in the traffic scene, and here we have two parts. So this was one of the cars that was cut up in two pieces. And if we start with the initial labels with the brush fire, you can see here we have nothing, 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 and then these are position 23, 24, 25, and so on. So if we run the brush fire algorithm on this, the code is repeated, but you can see here now that you needed, for this image, you needed actually 8 iterations. And you can see how many changes you had in each iteration. And now let's see what it looks like. The brush fire is the image. And in the end, we have 2 labeled objects. An effect of brush fire is also that the labeled numbers, they are quite arbitrary. They are more or less given by the smallest pixel position in the object. And so there can be gaps in the label numbering. And now we just looked at a 3x3 neighborhood, but algorithm if you larger. And here we look at a 5x5 example. And when we run this, oh, it doesn't run. That was stupid. Then I need to go back. Hello. There's to tell what was supposed to happen. And let's just switch back to the slides again. Oh. So what was supposed to happen here is that now if you have a 5x5 neighborhood, the neighborhood would actually also span across this gap. So that would result in that we have the whole object here, or the 2 pieces were labeled as a single object. So that would be the effect of having a 5x5 neighborhood. If we look at a smaller neighborhood, in the original version we had the 8 connected neighborhood, and now we look at the smaller neighborhood, so the 4x4 connected neighborhood. Then the code looks more or less the same, and after running it, you can see now that Brushfire is giving us 3 items. And the reason is that this cross neighborhood cannot sense this piece here. So here you can see the effect of having different neighborhoods, and in the scikit image you have the 4 connected and the 8 connected neighborhoods. So behavior, and we can mimic the first behavior I described. And yeah, here you see a table of how many segments we produced with the different algorithms. And yeah, you see then that it's important to choose the right neighborhood. And now that we have labeled the data, the question is what we can measure actually from this. So we could, for example, look at the number of objects in each volume, each label. what I showed you before, actually. And to give it a metric size, do the volumes here. So you have a number of pixels, but what is the volume or area of this? You want to have it in, say, millimeters. Pixel size? Does that mean anything? So, is to multiply the number of found pixels by the pixel size, or actually pixel area or voxel volume. So if you know the pixel size, then you have an area for that, pixel size squared, or if you have a volume, then it's pixel size cubed, and that multiply by this number of pixels that you got. And, then for example, finding the surface area, you can use a combination of erosion and dilation, or dilation. So what you do is to get the surface area, you do once erode of the objects, and then you subtract the original shape, subtract the eroded one from that, and the thing you get is actually the perimeter of the object. So then you get the length. And then you have to count those again, of course. So what do you want to do? We want to, again, do some measurements, so maybe cells, or actually more important, something about cells. And so how do we do this? We have, for example, we can look at positions. That can be interesting. For example, if you want to look at how cells are clustering around different nutrition points on the Petri dish, for example, or if you want to look at velocities in some additive manufacturing object or in a metal cast, you want to see how many bubbles you have in different regions, then you can look for the object positions. And that is we can compute using the center of volume, and let's see, now we got just the objects here, and then we can compute the center in different ways. Or in principle, we compute, oops, there it is. The center of the image, of the object, is the average X position for every pixel that is assigned to a certain label. And then we have the next one is every Y coordinate which have this label. And with this, and of course Z if you have a three-dimensional image. So with these position averages, you can get the center of gravity. And here we have an example where we look at this averaging, and we get all the, first we look out for the coordinates in this case, tabulate them, and from those we can compute the averages. Doing it using a data frame is maybe not the most efficient way, but it's nice for the visualization here. So usually you would just sum up these values while you go, and getting the sums directly from the loop. But in this case, I just used the data frame to tabulate and show that we can find the pixel positions of each pixel in the object, and when we compute the average of these positions and average of these positions, we position our center of gravity in this spot. Also compute center of mass, and that is a little bit an extension of that, and the center of mass is that you weight in the gray level that you have the object. So now we are computing actually the average gray level in the image. And that gives, let's see, yeah. Let's just produce some images. So we have the segmented image like this, and then we have some intensity image where you have dark up here is great values, and brighter values are low. Brighter points are low value. And if we now compute of mass and center of gravity on these, we get these sums here and compute the average values. And from that, we can get of the volume is, as you expect, in the middle of the image. But if you start weighting it with the gray levels, you see that there is a trend pushing towards the darker corner, because have a higher weight, and then they get so we have seen we can measure a lot of information. We can measure the area. Sphericity is something that we can look at. Sphericity is more or less the perimeter, no, the volume over the perimeter or surface area, and that gives you a metric that tells how spherical the object is. We can also measure the orientation, and that's so usual that people want to do this, so that's already implemented in scikit-image. And there is a function called region props that you only feed the image, the labeled image, and as a second parameter you can also feed the intensity image if you want that. Yeah, we have the, let's see, the manual page of it, and you can see down here a big collection of different values that you can get. You can get the area of the actual label pixels, you can get the area of the bounding box, and the bounding box is the box that where the that inscribes the whole object, and there can be some white areas and then some object areas within it, but it's a box that covers the whole thing. And you can get the centroid, you can get the axis, minor and major and minor, eccentricity, and a lot of other numbers within these regions. So this is quite convenient to work with. If we look at the car image, or let's see, is it the car? Yeah, it's the car image. And here we now can go through and look at what different areas we have in what object is this. And here you can see all the values that you can list from this. So this is quite convenient to start working with labeled images. Problem is, this is a lot of information, and some of it is too abstract, too specific. Doesn't have really a relation exactly to what you want to know. So, for example, if you look at some cell, asking what is the length in the x direction, that's a useless information, actually, because if the cell is a little bit ellipsoid and it's tilted, direction doesn't mean anything. You really have to look into the right properties and use them in the right way. In the case of the cell, we would probably more look like at something like the major and minor axis instead of length in a certain direction. And the extents, that is essentially the bounding box that I already mentioned. So it is for each direction looking for the maximum coordinate minus the minimum coordinate in the x direction, and the same for x and for y and z. And what it gives us, what it looks like, is here we actually computed the whole thing. This is, say, the most obvious way of implementing it, but not the most efficient. So there are different ways of doing it. And afterwards, we can get this rectangle. And yeah, this is mainly just visualization code. But the interesting thing is that you can see here how you can add, for example, rectangles to the image, marking out the regions, something that can be useful. Backtracking on what you're doing, but also sometimes for publications to show this is the region that I found. And now we can look at properties of this city scene with the cars. We have labeled our images, and now we can look at a lot of properties. We can put in the bounding boxes. We can put label colors just as a getting the centroids. And what more? We can also get the average color within these regions. And then we need a little bit of help of web color database and use a K-neighbors classifier. And with K-neighbors classifier, we have in each region of interest or in each object, we have an average color code, so some RGB code. And with the help of k-means, we can find the web color that is the closest to it, because we can call this web color database as our pre-trained object, and with the k-means, k-neighbors, we color that is closest, and then we can actually give each color here some name. So this is a way of how you can put names on colors. And yeah, so most of them are actually gray, which is quite boring. And I think there isn't there. Yeah, there is one blue and one is silver. So as usual, most cars are actually gray and silver. So that makes kind of sense. Yeah. Then before the break, I want also to talk about object anisotropy. What is it? Have objects, well, in the nice ideal world, we have only circles, but normal objects, they are not. So what can we have? We have, for example, tall and skinny. We can have short and fat. We can have perfectly round. These are shapes, and they are subjective descriptions. But can we put a number on it? What we can do by the anisotropy. The problem is that this description actually depends on what you want to know. How do you define the metric for it? You can describe it as the longest side divided by the shortest side minus 1. You can have the difference divided by the longest. You can have the average, and so on. You can find up some kind of definition. How can you describe the anisotropy? And that probably relates more to your field of research, where you are. What is your definition of anisotropy? So you can do a lot of different metrics here. And here we have defined different anisotropy functions given the region of the bounding box for some object here. And looking at the table, yeah, this is when we have a circle that we shift on to being more and more ellipsoid until it's essentially a line. And then you can see what the different anisotropy metrics, what they are doing. Some are more sensitive, some are less sensitive. And the question is what you really need in your investigation, how sensitive you should be, in which ratio area region. So sometimes you want a specific target. some kind of ellipsoid shape with higher precision, then you may go for a different metric than if you want to go all the way from the circle to the line. The good thing here is that these metrics are actually orientation insensitive, so the orientation shouldn't be involved in these metrics. And that is something I actually keep till after the break.